Hello, technophiles. Welcome back to Techno Fame, the place where complex technology is made simple. I'm your name, and today we're kicking off a comprehensive journey into high-voltage engineering, what it is, why it matters, and how it impacts everything from power grids to your electric gadget charging at home. If you're curious about how electricity moves over long distances, how insulation can fail under extreme stress, or how engineers keep everything safe, you're in the right place. In this video, we'll cover a bit of history, how and why high-voltage engineering evolved, core fundamentals, voltage, electric fields, dielectric strength, insulation, materials, breakdown mechanisms, how we generate, transmit, and distribute power using high-voltage systems, safety, testing, and engineering standards, applications, and future trends. So grab a notebook or open your mental notebook, hit like and subscribe to Techno Fame if you haven't yet. Let's dive in. Let's rewind a bit. Electricity is not new, but high-voltage techniques are relatively newer in terms of practical, large-scale use. Early experiments. Scientists like Volta, Faraday, Maxwell laid the groundwork for what voltage and electric magnetic fields are. Then in the late 19th and early 20th centuries, as cities grew, factories demanded more power and distances increased. The need for efficient transmission of electricity over long distances became acute. The problem: power losses are proportional to current squared I2R losses. If you try to push large power over long wires at low voltage, current is huge. Big losses and big wires needed. The solution: increase voltage. Transmit at high voltage so current is lower for same power. Use step-up and step-down transformers to manage at both ends. Over time, this led to development of high-voltage AC systems, then HVDC, improved insulation materials, standards, safety procedures. And now, with renewable power sources often located far from load centers, for example, solar farms in deserts or wind farms offshore, high voltage becomes even more critical. Before going deeper, let's nail down some core terms and physical principles. Voltage, potential difference. Voltage is electric potential difference between 2 points. It's what pushes charge, measured in volts, V. When we say high voltage, we usually refer to voltages in the kilovolt, kV, megavolt, MV scale. In many contexts, AC above 1 kV or DC above tilde 1.5-3 kV is considered high voltage, though definitions vary by region. Electric field. Field strength, E, is force per unit charge. When you have two conductors with a difference in potential, an electric field is set up. High electric field strength can stress materials, especially insulation. Dielectric insulator. These are materials that do not conduct electricity, or conduct very poorly. Their job is to resist current flow, preventing breakdown. Important properties: dielectric constant, dielectric strength, maximum electric field before breakdown, loss tangent, thermal stability. Breakdown mechanisms. When the electric field or voltage gets too high, insulators fail. This can be via dielectric breakdown, surface breakdown, creepage, corona discharge, partial discharge, or flashover. Each has different characteristics. Types of high voltage: AC versus DC, alternating versus direct current. Each has pros and cons at high voltage. For example, skin effect, ionization, corona. Impulse voltages, very short duration high voltages. Think lightning or switching surges. Concepts of stress grading, field uniformity. Since insulators fail more easily at points of high field concentration, sharp edges, points, engineers use design techniques to distribute field uniformly. Field grading, rounded edges, corona rings, etc. One of the most critical parts of high-voltage engineering is insulation. Without solid, reliable insulation, everything fails. Types of insulating media: gaseous insulators, air, nitrogen, SF6, sulfur hexafluoride, etc. SF6 has excellent dielectric strength but environmental concerns. Liquid dielectrics. Transformer oil, insulating oils, used for cooling and insulation. The dielectric strength is often higher than air. Solid insulators, paper, polymer, for example epoxy, silicone, polyethylene, ceramics, mica, etc. Properties to consider. Dielectric strength, maximum field before breakdown. Permittivity, how well the material polarizes in field. Dielectric loss, how much energy is lost as heat. Thermal stability, aging, moisture absorption. Failure, breakdown mechanisms. Uniform breakdown when the field is too large throughout. Partial discharge, small discharges that don't bridge electrodes. They degrade insulation over time. Surface breakdown, along surfaces. Creepage and tracking. When contaminants, humidity create conductive paths over insulator surfaces. Corona discharge, localized ionization of air when field is strong near sharp edges, leads to noise, loss, ozone, etc. Design considerations and prevention. Use insulation with higher dielectric strength. Proper shape. Geometry. Avoid sharp edges. Smooth electrodes. Corona rings. Control of environment. Clean, dry, prevent contamination. Grading of insulation, for example, solid liquid or solid gas interfaces. Now that we understand the materials and physics, let's see how high voltage is used in real systems. Power generation to transmission. Power is generated typically at medium or low voltage, for example, a few kV in power plants. To transmit large powers over long distances, voltage is stepped up using transformers to high or extra high voltages, tens or hundreds of kV. AC, alternating current, has been standard for over a century for transmission due to ease of transforming voltages. HVDC, high voltage direct current. For very long distances, approximately 600 km for overhead lines or ~50-80 km for submarine cables, HVDC can be more efficient. Less reactive losses, no skin effect, can interconnect unsynchronized grids. But conversion stations, AC to DC and DC to AC, add complexity and cost. Transmission and distribution levels. Extra high voltage, EHV, typically 230 kV up to 765 kV or more in many countries. Subtransmission, intermediate levels. Distribution, stepping down for industrial, commercial, residential use. Components in the chain. Transformers, step up, step down. Transmission towers, conductors, insulators, switchgear. Substations, AC and/or DC. Protection devices, circuit breakers, isolators, surge arresters. Losses in transmission, resistive I2R losses, corona losses in high voltage overhead lines. Dielectric losses, reactive power issues for AC. Strategies to reduce losses, using higher voltages, using conductors with larger cross-section or better material, using bundled conductors, improving insulation and minimizing corona, HVDC lines in appropriate cases. High voltage is powerful but dangerous. Safety is not optional. Engineering standards, testing, and operating procedures are critical. Health and safety risks, electric shock, arc flash, burns, electromagnetic fields, EMF. Insulator failures can lead to fire or explosions. Environmental hazards, for example, SF6 gas leakage, ozone from corona. Safety practices, proper PPE, personal protective equipment, insulated gloves, boots, face shields, flame-resistant clothing, safe clearance distances, grounding, earthing of equipment, warning signs, exclusion zones, regular maintenance and inspection, standards and regulatory bodies, International IEC, International Electrotechnical Commission, IE, Institute of Electrical and Electronics Engineers, etc., national standards, for example BIS in India, IEC's adoption, etc., codes for voltage levels, insulation, testing, safety. High voltage engineering isn't static. New applications and challenges keep appearing. Some current and emerging applications, long-distance transmission via HVDC, like cross-sea cables linking remote solar farms. Interconnecting grids, even between countries, using ultra-high voltage, UHV lines. Renewable energy, offshore wind, deserts, solar farms far from load centers. Electric transportation, high voltage in electric trains, metros, even future Hyperloop, etc. High voltage in particle accelerators, medical devices, X-ray high-tension supplies, etc. Emerging trends, research areas, new insulation materials, nanocomposites, more environmentally friendly gases than SF6, improved polymers. Monitoring and diagnostics, using sensors, IoT, predictive maintenance, real-time partial discharge detection. Smart grid integration, handling fluctuation in power generation, solar wind. Integrating storage, handling DC microgrids. Environmental concerns, reducing losses, mitigating corona noise ozone, greenhouse gas emissions from insulating gases, visual impact of large towers. All right, technophiles, let's wrap up what we've covered. Key takeaways. High voltage engineering is essential whenever we need to transmit or use large amounts of electric power efficiently and safely. The choice of insulation material, geometry, and design is crucial to prevent breakdown and failure. Transmission, AC or DC, system components, losses, and standards all interplay to determine how reliable and efficient a system is. Safety is paramount. Standards, testing, and careful design protect people and equipment. And as we move into a more electrified, renewable energy-dominated future, high-voltage engineering will be more important than ever. Let me know in the comments, what topic do you want me to cover first? Which test or concept confused you most? Hit like if you found this helpful, share if you think others studying engineering will benefit, and don't forget to subscribe and ring that bell so you don't miss the next episode. Thanks for watching TechnoFame. Electrify your mind, engineer your future. See you in the next one.